So I would like you to guess now what the sufficient statistics would be for this example. Suppose my samples come from a uniform distribution from 0 to theta, and theta is my unknown parameter that I want to come up with a maximum likelihood estimate. Okay? So again, I have a sample from a uniform distribution from 0 to theta. So this is actually my likelihood, the way it looks like. This is the indicator function, right? So if xi is from 0 to theta, by the way, uniform distribution means 1 over theta, but obviously xi needs to be on the interval 0 to theta. Okay, so this is an indicator function that multiplies 1 over theta. And if I have n data set, n points, I can write this as such. Do you agree with this? So if I take all of this and multiply them together, can I write them like that? From where is that coming? Remember, this will be, all of these terms will be, that come in this product basically, will be non-zero if xi is from 0 to theta. So theta has to be from where to where? From a maximum of xi to infinity. So what's the sufficient statistic for the calculation of theta if I do maximum likelihood estimation here? Maximum of xi. Nice. All right. So things can be weird looking. Okay. Now I'm going to jump to slide 14. There are many more examples in the notes that you should consult so you can get a good idea of the sufficient statistics. So let me state the sufficiency principle. Okay, so let me read it. If you have two observations, x and y, that have the same values of sufficient statistics, okay, then the inferences about the parameter theta based on x and y need to be the same. I repeat, if you do two experiments, right, you collect data x and data y, and they have the same sufficient statistics, then when you do inference about the parameter theta of the distribution, all right, then the two inferences have to give you the same value of theta. So if you do, let's say, maximum likelihood estimation, you should get the same if you use x, the same if you use y. And again, that's a common sense because we said that what defines the estimate of theta is the sufficient statistics. Obviously, if they're the same, then the same estimate will come out from this for theta. And here is a proof, for a simple case. Let's say we have samples from a Gaussian, and to make things simple, we take the variance to be known, equal to 1. So the only sufficient statistic is the sum of the xj's. So if somebody tells you, you collect some data xj and some data xj prime, and the summation, this summation is equal to the summation of xj prime, then the MLE estimate needs to be the same, which is no problem because remember the MLE estimate for the Gaussian is the sample mean. So you have this divided by n, and obviously this divided by n is the same as xj prime divided by n, summation, all right? So the two estimates are the same. Now you may say this is, obvious, yeah, but I'm not going to go through. On the bottom of the slide, I have another estimate because, you can come up with your own estimator for the parameter theta, in this case, the parameter mu, right? That violates the sufficiency principle, okay? So don't take that every estimator that you come up with satisfies this, but you need to be sure that it does. Okay, so we're slide 14. I'm going to jump to slide 17. Another principle that we need to be sure that is satisfied, and again, it's a common sense principle. In the inference about the parameter theta, the information brought by an observation is entirely contained in the likelihood function f of x given theta. I mean, obviously, we work up to now, we haven't really done anything else with the MLE estimate, right, by maximizing the likelihood. But the likelihood principle tells you the information that comes from any data point is contained entirely in the likelihood function. And obviously this implies that if I have two likelihood functions that they are the same, I better get the same estimate, or that they are proportional to each other. I mean, if they're the same, it's not an issue. If they're proportional to each other, then my estimate for the parameters theta needs to be the same. So if you have a likelihood that looks like some function of x times another likelihood function, the estimation, when you do maximum likelihood, for example, the estimate that you get for theta from here and from there has to be the same. Is it? So if I maximize this function with respect to theta, do I get the same thing as maximizing this with respect to theta? Yeah, because C of x does not depend on theta, okay? And I refer now to maximum likelihood estimation, right? But obviously, we're going to do lots of different types of estimations in this course, and we only have seen maximum likelihood, and that's why I refer to it. But basically, any sort of estimate that you come up for these parameters needs to satisfy this likelihood principle. Okay. Now, you remember I told you that I would not emphasize the standard statistics that you maybe learned in other courses, or maybe you are still learning taking course in ACMS and elsewhere, all right? Most of the non-Bayesian statistics does not satisfy the likelihood principle, okay? And I'm not going to elaborate on it, but for example, for those who know ideas of, and I put those things last night on p-values in the slides, in a lot of calculations that you do in non-Bayesian statistics, you integrate over the data space beyond the observed data, basically. You do calculations that don't necessarily involve the observed data, and all of those calculations do not obey the likelihood principle. And I have a very nice example of two distributions in the notes that have proportional likelihoods, but when you do compute the integrals like this, they will basically give you different sort of, this will not be estimation of parameters, but maybe different decisions that you will make out of this analysis. Okay. I'm going to give you one example that is the most famous example in the literature on why you really need to be Bayesian, okay? It's one of these simple examples. By the way, if anybody has time, the website of Professor Vidakovic from Georgia Tech has a lot of nice sort of lecture notes if you want to visit on this type of calculations. So let me do a simple example to demonstrate how you can be in trouble with this likelihood principle. Let's say that we take samples from a binomial distribution. So, you know, you fix the number of coin flips, all right? And you want to decide if the coin is fair or not, okay? So theta is the probability of being heads. And so fair means theta equal to 1/2. This is the alternative hypothesis, theta greater than 1/2. So we predetermine, this is important, but our experiment will be that we will do 12 flips of the coin. So we do 12 and we collect data x equal to 9 heads. So the likelihood looks like that. Everybody agrees? Okay? All right, so out of 12, 9 is heads, so theta to the 9th, 1 minus theta, 12 minus 9. It looks like that. All right. In non-Bayesian statistics, to decide if the coin is basically fair or not, you calculate the probability of observing data, in this case x equal to 9, but also extreme data, so for x greater or equal to 9. Okay? So in essence, you're going to have to sum this for x equal to 9 and x equal to 10 and 11 and 12. Okay? So this is what is called the p-value that people in non-Bayesian statistics compute. And in this case, the p-value comes to be below